Oh, welcome everybody. Welcome to the rabbit hole. I'm Joe Slick, and my guest tonight is New Brunswick, Canada guy, better known as Canuck, as I call him. Only reason because it's easier to say than New Brunswick, Canada guy. But we're looking here at the tonight's forecast for the auroras. If you're way up the north next to the border, you might see them in the northern hemisphere. But those people who are with us here, we did have an X flare, an X 1.83 here 12 hours ago or 11 hours ago, and 1, 2, 3, near 4 M flares right afterward, and it's still an elevated status, almost an M status. Probably it's just a C4, 481, so almost a C1 or C5. So that's the current status. The Space Weather Prediction Center says we are at a 4.2 KP index. The radiation level is high for those people who are flying. Don't fly. You're more apt to get more of a dose of radiation, and because it is above that certain level, the warning threshold. The flare or the X flare that popped, there's the halo that popped at us. And watch, you'll see, boom, there it is. So big X flare again. That's the second X flare in how many days? 2 days. So that's pretty wild. And this is the disk, and I'll push go. You can see where it flashed. And probably right over here. Huh. I didn't see it fall. Maybe a little one. Nothing to worry about. Space weather right now says the solar wind is 460. The proton density is 5.63. C9 and the next one in the last 48. An X flare doubles. Look at this. Boom. Big boom. Share this tab instead. So you okay? There it is. Kablam. Big flare. A lot of plasma being shot out. Minor CME impact would just happened against our planet. It grazed us on the 26th. The impact was weak, barely increasing the solar winds, and nevertheless, the geomagnetic storms are still possible for the next foreseeable future. Real short, really. 3872 is beta gamma delta magnetic field. It harbors energy for X flares. So number 72. Where is 72? Where are you, 72? Right there in the middle. All right, so you know that. All right, and yeah, all right. So we've touched base with all that stuff. What else we have? And let's see if there's any pressure. Share this tab instead. Here's the magnetopause model. Dynamic pressure is up a little bit. That's what I was wondering. The BZ is in the northern hemisphere. Proton density stays around 9, but the wind is at 438 currently. So if we push play, you see still banged up a little bit. Interesting. That's the new day. That's just starting on the 27th. So we'd have to go back to the 26th. So if I did the 26th, you'll see that's where we're at. So push play the whole day. You'll see the solar wind stays down around 300. Dynamic pressure stays under 1. The standoff distance stays around 12. BZ, I went up to -9 or -10, so that would tell us that something's happening in the southern head. Looked like a 12 there. Yeah. So there's some energy, hitting our planet, absorbing by the ionosphere. And I see my boys out there, interplanetary field 2820 to the north. Yeah, right now it's at 4.8 interplanetary magnetic field BT. Yeah. So, doing all that. So looks okay. Tremors in the Pacific Northwest. Let's see. We don't have any for today. 26 of them from yesterday, or today actually. And the buoys. We had some buoys bouncing around here over the last, as that hurricane gets out there. Hurricane Christy, look out. And the buoys are stopped. especially this one that was up here. Yeah, yeah. And over here, see anyone's out here. I don't see any buoys activated, which is good. So not much happened, but it's a little bit of vibrations south of Trinity National Forest and south of Shasta. So that's happening in the world today. I noticed this afternoon we had a pretty good earthquake out in the mid-Atlantic. Central. I call it the central, but it's in the north. It's a 5.0, so that should tell us something about what's happening across the plate, our plate, North American plate. All right, so be watching. Interesting to see what happens in Costa Rica and southern Mexico. And then when we get up and we notice that Long Valley had a 2.5 today. Pretty far out. Yeah, so no, it wasn't this afternoon. It just happened 51 minutes ago while we were waiting. So we had the Long Valley quake and then the North Atlantic. And the North Atlantic quake is important, not significant, but important because of what we're discussing. So we'll bring that up when we get there. Let's see if there's anything else very significant that popped as I zoom through that.
Popo.
Yeah. Popo is going just a little bit. 4.2 Veracruz. 4.0 off the coast of Costa Rica. There's a earlier 4 hours ago. Chiapas, Mexico, 4.3. And we're going to look at 4.0 San Juan, Argentina. 4.3 Isuzu Islands, Japan. And then southern Iran had a 4.2. Let's go ahead and look at volcano news real quick. And looking specifically at Nyiragongo, eruption continues. 23 out of Nevada del Ruiz, that's not a lot. Simeru, that's not a lot. Shivalush, not identifiable. Sunozajima erupted 7,000. That's 2,800 going to 7,000. So that's not a lot. Popo, 30,000 feet. That's significant boomer right there. And that's not the only time it's done it. So it's a 17.8, 17.9 going to 30,000. So it doubled its size. And Popo's been super quiet. So it's clearing its throat. It's clearing its throat. So they're probably having a little bit of danger. I saw the reports yesterday when it exploded. Did you see anything significant, Canuck, on Popo?
No, I just saw pictures of it on one of the other things I was watching. And Marapi going up. I don't know if it was Marapi or
Merapi. All right, we'll look at it. There's Merapi, that's MA, then there's Merapi. Merapi's on Sumatra, Merapi's on Java. Popocatépetl is basically Mexico City, everybody, if you didn't know that. We're taking a quick look through here. 30,000 feet is pretty damn big. That's the largest we've had in a couple of months for sure. Shivalush not identified. Manam volcano as well. Ground estimate, maybe
so PNG.
Yeah, just a little bit. It's not saying what the height is though. But generally, Manam volcano does not. You just sit there and fart in the wind. When it blows, it goes pretty good, 30,000 plus, and then it shuts up for a while. So it builds up pressure, releases it, just like Popo's doing right now. The chicken leg is moving, so I think that's why Popo is burping. Dacono is 8,000. Little Toby is 7,000. So Little Toby in just north of Timor. Popo, I guess it's been bringing when every time it says Popo at 30,000 feet, those are each eruptions. So it's multiple eruptions in one day popping to 30,000 feet. And 8,000 Ibu on Halamarahara. 20,000 Sengay. What? Yeah, Sengay is 17 going to 20-0. and Simi Route. Well, that's what's going on. So yesterday, intense activity still near Magura, and that's in Africa, Ethiopia, and it's smoking. You can see. I can't really tell much out of that. 32,000 for Popo yesterday. So it's got 2 days of 30,000 plus eruptions. 14, 20. I'm just skimming these just so we can get started with our show tonight. But everybody, I wanted to tell you that what's going on too as we skim the data. Popo 24,000. So it started yesterday about 24,000. I saw it doing like 22, 24, and then it's going to 30. So that's pretty significant jump. And Dakota 90. This is on Friday, by the way. 15. So not, and that's it. So Popo is really active, and we'll be watching that. And Nepal had a 4.0 as well. Southern Iran had a 4.2. And let's see here. 4.3 out of Isuzu Islands, Japan. 4.2 Philippines, off the east coast of Kamchatka, 4.2. Remember, what's happening in Kamchatka is Shivalush and Bezimani. Well, both of those are banging away. So is that one that's in the south on that little island. I forget what it's called. But anyway, we'll come across it if it does. Celeb C had a 4.3 as well. 4.6 out of the Flores region. That's above Simiru. Behind Simiru and above Java. Basically, Indonesia is made into two huge islands, and then a bunch of little ones that go north on the northeast side. So Java, and what's between Java and Sumatra, where Sumatra had the big earthquake way back in 2010 or 2012, one of the two. Krakatau is between the two islands. So we watched that as well. Tonga 4.4, Kapilan Babar, which is up by Hanamahara, 4.6. Ethiopia had a 5. Wow, all right. And we're back 14 hours. Gulf of Cali did have a 3.4 early this morning. Southern Cal had a 2.0 as well. So it was really early in the mornings. Colima, Mexico had a 3.3. Northern Cal 2.4. Northern Cal had an offshore 4 and a 4.1. So that's 16 hours ago. So last night or yesterday afternoon, California was banging. Bang, bang, bang. 3 of them. Mm-hmm. Offshore Northern Cal. And also offshore Central America, which is a little 3. But Southern Xinjiang, China, 5.1. And that's enough. So we'll be watching what's going on. We'll bring that here as we're looking at JSL. Good evening, JSL. God, don't notice. Yeah, don't worry about it. Here we are. Looks like it works for me. My end when he goes live. We're already live, baby. You send out notifications to say that when you're going live. Yeah, thing goes live. Yeah. There we go. Luke, you also have the link if you want to join in. Tonight, let me go grab this one. That's joining. What am I doing? That's not the right one. Canuck. Oh crap. All right.
You sent it to me, probably.
Why'd you send the link to me? You sent it to yourself. You sent it to me.
I cut to my thing because I put in so many. It was there 2 million.
Oh, you did it today?
Above, so
all these. Oh, you did. All these are. All right. Let me put them in order.
Yeah.
All right. Just bear with me. Dun, 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 dun.
I just did all them like an hour ago, put them all in order.
All right, bud.
Because I had way too many. So.
Yeah, I know how that is. And like I said, I think I kind of changed up a little bit. We'll do the shears on another date, but I think you have plenty right here. I'm looking at all these. Wow. And we're going to jump right into it. So, God, you have a lot of links.
And the one Quake Cat put in there is good too. So it just gave me more things to look up.
All right. So first one. Okay, we got this one is your first one you put on. All right. I just closed.
Yeah, which is the same map we started with.
All right. So I mean, here we go. I got to do this way. So go here, share my screen for everybody else. Index map. Here we go. This is one we were working with the other night. And what's going on? Okay, show this on stream. There we go. All right, Canuck. There we go. So let's go ahead and get right into it. Oh,
yeah.
What happened?
So we're actually going to start with Garlock tonight, but I wanted this map up just because it reviews what ones we talked about last episode. So it's got all the southern East California shear zone faults. So now we're starting with Garlock, which technically is central of the Eastern California shear zone.
Right, right in the middle. All right, so let me.
Yeah, and basically anything above Garlock, they also consider Walker Lane. So we're kind of doing a bit of Walker Lane tonight too. Okay. The official one.
The official Walker Lane. Not the Joe Canuck
the official
Walker Lane.
The official one is in California.
Yeah.
And Nevada and a little bit up in Oregon. But my version is a lot bigger, but that's another story.
All right, so right here's the Garlock, everybody. As you can see on your screen, I'm going to zoom in just like I learned how to do this. Here's Garlock right here. We've talked about all of these faults in the south, all of these. We talked about the different faults offshore and how they function. As we go above the Garlock, we also will touch on some of these that go up toward San Francisco. We'll probably do that next time around, but we're going to talk about this area right here tonight. All right. It's three main valleys: the Owens Valley, the Panamint Valley, and Death Valley, which is the longest of all of them, next to Owens Valley, which is yeah. All right. So on that index map, share this tab instead. You'll see that right here in this area here is what we're talking about. All right. Continue there, Canuck.
Yeah, so we're just going to do the wiki next because it's pretty short.
There's Garlock. So share this tab instead. Sorry about that. The Garlock fault is a left lateral strike slip fault running northeast to southwest along the north margins of the Mojave Desert of Southern California for much of its length along the southern base of the Tehachapi Mountains. All right. This is the Garlock fault, looking at it. And and going back. And then you'll see this is the Garlock fault right through here. And that's what we're going to be talking about. It stretches 250 kilometers or 160 miles. It is second longest fault in California and one of the most prominent geologic features in the southern part of the state. It marks the northern boundary of the area known as the Mojave Block, as well as the southern ends of the Sierra Nevada and the valleys of Westmoreland Basin and Range Province. Garlock Fault runs from a junction with the San Andreas Fault in the Antelope Valley, eastward to a junction with Death Valley Fault Zone, the eastern Mojave Desert. Okay, so in the eastern Mojave Desert. It is named after the historic mining town of Garlock, founded in 1894 by Eugene Garlock, and now a ghost town. Relatively few communities directly along the Garlock, as it is primarily situated in the desert, with Fraser Park, Tehachapi, Mojave, and Johannesburg being the closest towns to it. The geology of the Garlock Fault is believed to have developed to accommodate the strain between the extensional tectonics of the Great Basin crust and the right lateral strike-slip faulting of the Mojave Desert crust. Unlike most other faults, California's slip on the Garlock is left lateral. That is, the land on the other side of the fault moves to the left from the perspective of someone facing the fault. Thus, the terrain north of the fault is moving westward on that south, and that on the south is moving eastward. So basically, everything south of Garlock is moving out toward North America. Everything above it is moving out toward the ocean. Okay. So, any more you want me to continue, or?
Yeah.
Okay. The Garlock fault moves at a rate between 2 and 11 millimeters a year, and its average slip is around 7 millimeters. While most of the fault is locked, certain segments have been shown to move by seismic creep, which is vibrations, which is a motion without resulting earthquakes. The Garlock is considered to be particularly active fault, seldom producing any shaking detectable by humans. It is not considered particularly active, okay? I misspoke. Although it has been known to generate sympathetic seismic events when triggered by other earthquakes, and one instance by the removal of groundwater. These events is well-known continuing micro-earthquake activity, and the state of the scarps from previous ruptures do indicate that the Garlock will produce another major quake at some time in the future. A study published in 2019 in the Journal of Science indicated that the Garlock fault slip, after being triggered by the series of earthquakes in Ridgecrest, which occurred in 2019 of July, reports that in the Los Angeles Times indicate that the magnitude 8 earthquake along Garlock Fault would have the potential for grave disaster. Did you hear what he said? It could be an 8 on the Garlock. The last significant rupture on the Garlock Fault.
I think it can go 8-1 or 8-2.
I'm sorry, you broke up.
They think it can go 8-1 or 8-2.
Okay.
They think it can go 8-1 or 8-2 now in
the
studies.
The last,
so like similar to the southern San Andreas.
Okay. Now, the last significant rupture on the Garlock was thought to be about 1050 AD or 1500 AD. Research has pinned the interval between the significant ruptures on the Garlock as being anywhere between 200 and 3,000 years, depending on the segment of the fault. The most recent notable earthquake fault zone was a magnitude 5.7 near the town of Mojave on July 11th, 1992. It is thought to have been triggered by the Landers earthquake just 2 weeks earlier. However, no surface slippage of the fault itself had been recorded in modern times until 2019. Following a series of earthquakes, the nearby minor faults in the July 29, the Garlock Fault was observed moving about 2 centimeters. That's a hell of a lot more than 2 millimeters, 2 centimeters, between July and October, accompanied by the numerous minor earthquakes, a state known as fault creep, and producing a bulge in the observed satellite radar images. Yeah, so so they can test all that. So what Landers did in 1992 is it moved in the desert 17 feet, and it rose like 9 feet, I think. But Garlock also is responding to it, and that's what they're saying. It moved 2 centimeters. So a big 7.3 moved Garlock 2 centimeters. It's pretty locked up, in my opinion. But go ahead there, Canuck, if you have anything left.
Yeah. Now, that stuff I just talked about at the end is important with the next two studies we're going to look at.
Okay.
Because they're like brand new ones. The first one is from 2023.
Okay, the evolution slip. Yeah,
should be the next one.
March 9th. Yeah, share this tab instead.
Yeah.
Evolution slip partitioning in the major continental margin slip, strike slip fault system during the transition to oblique plate margin tectonics. Insights into the evolution of the Garlock fault zone, California. And do you want to read it or you want me?
I'll read the abstract part. We're not going to go super deep into this one.
Okay.
I like the maps. That's why I picked this one.
Yeah, I got the map on
the Walker Lane Belt, the eastern shear zone of California, USA, are active plate boundary related dextral systems with transtensional and transpressional deformation, respectively. They are separated by the sinistral Garlock fault, creating a complex system without an overall integrated formation and evolution model. We examine the deformation within the eastern segment of the Garlock fault zone over geological timescales by determining the slip history of faults. Now, I'm going to read more, but I'm just going to explain. Mm-hmm. Like right now, all these newest ones, they're taking segments of the fault, depending on how many segments they decided are in it. Now, Garlock, they've broken it into three: Western, Central, and Eastern. So you'll see what this means the farther we go into it.
Okay.
So they're obsessed with figuring out the slip rates. Yeah. Mm-hmm. So we assess the progression of faulting and associated deformation along the west-southwest striking Garlock fault zone and how it applies to the overall north-northwest directed dextral system. Previous studies found that large synthetic fault strands take up to 30% of the slip of the Garlock fault zone and have proposed multiple mechanisms to explore how to accommodate regional north-northwest directed shear across the Garlock fault without cutting its trace. We analyze an unstudied section of faulting in one of the more areas of the regional deformation via compiled and reinterpreted published geological data for an analysis of total and incremental slip on the main faults of the eastern Garlock fault zone. We identified geological offset features to interpret total slip, timing, and deformation evolution. We find that 30% of the total slip of the Garlock zone occurs on strands other than the Garlock fault sensu stricto, with the focus of main slip sidestepping the evolution of accommodation of through-going regional dextral shear. Our results support ideas of the creation and evolution of the regional dextral system via stress concentration on a sub-Garlock lithospheric anisotropy, with result lowering of the plastic yield stress. Our results show an eastward increase in fault system complexity, which may imply an underappreciated seismic hazard of the eastern Garlock fault zone. Now, I'm just going to stop. I'm going to read more after, but I kind of want to explain what they're saying. Mm-hmm. Now, the eastern section, which is the farthest one out, goes to Death Valley. That's the one they've studied the least. So that's why I picked this study.
Okay.
Now, previously, they've been focused on the very west section because...
You're breaking up for some reason. I don't know what's going on. I think we may have lost him.
Oh, okay.
You're there.
Now,
you're there. I can hear you.
Still hear me? Okay.
Yeah.
Yeah. And now since 2019 and the Ridgecrest quakes, they've been focusing on the central section, trying to figure out how much it slipped. So this is all the stuff they're talking about. So now they're trying to put what they know from the western section, the central section, and now the eastern section all together.
Mm-hmm.
Yep. Now, in this next section, it talks about other places, like where it does something similar. So I'm going to start with the second one. This study examines the fault slip history of an area within a well-exposed and well-studied zone of continuing dextral deformation in Eastern California, USA. We discuss the Garlock Fault Zone, our large transversely oriented set of sinistral strike slip faults. These faults separate the trans-tensional Walker Lane from the trans-pressional Eastern California shear zone. So see, they're saying anything, and the other stuff.
I'm sorry, I didn't hear what you said. You said you broke up. I think it's when you talk very loud, your microphone has a suppression. So if you talk really loud, it'll break it off. So you just got to talk really kind of chill.
Yeah. So basically what they're saying is Walker Lane, for the purpose of this study, is north of Garlock, and the Eastern California shear zone is below it, so south of it. So that's what they're trying to say. I like how they use all these.
Can you repeat that again?
So what they're saying, they're talking about these faults separate the trans-tensional Walker Lane belt from the trans-pressional Eastern California shear zone. So they're talking about Walker Lane above it is trans-tensional, and the Eastern California shear zone is trans-pressional. So I think that's pretty
okay. That's kind of defines the differences between. So north of Garlock is the Walker Lane belt, and south
that's what they call it for the purpose of
this. Yeah.
Because I've heard ones that include it all together as Walker Lane, and other ones that don't. So it just depends on how they view it, I guess. And it says our goal is to determine the deformation history of the Garlock Fault Zone in the context of regional deformation and how slip on this non-ideally oriented fault functions in the deformation zone in which it is embedded. This study interpreted in history using identified offsets of geologic markers for faults in the eastern segment of the Garlock Fault Zone to examine accommodation mechanisms of the north-northwest directed regional shear crossing the continuous trace west-south fault. And so now the next
our goal
paragraph,
is to determine the deformation history of the Garlock Fault Zone in the context of regional deformation and how the slip broke on this non-ideally oriented fault, because something is about is not ideal in the deformation zone, which is embedded. So it's in the middle of something and it's not ideal. The study interprets the slip magnitude and history of using identified offsets of geologic markers for the faults in the eastern segment of the Garlock Fault Zone, and to examine accommodation mechanisms of the north-northwest directed regional shear crossing the continuous trace west-southwest striking Garlock Fault. West-southwest. Okay, so they're coming out of the east with the west-southwest striking fault. And the north-northwest, well, see, the north-northwest side of it is going westward, and the other part's going eastward. So this portion down here on this map, I know you can barely see, from these dotted line, that's the fault. It's going to the right, and everything above it's going to the left, which we all know because we studied Ridgecrest plenty of times, those who have joined us. So if you want to continue, go right ahead.
Yeah, we're just going to finish this section. A note on the terminology used in this paper: the Walker Lane Belt and Eastern California Shear Zone labels are very applied to this zone of dextral deformation. So it's basically saying what I already said already, that the Walker Lane and Eastern California Shear Zone, they disagree on what should be separated or two together. To honor the original definitions and simplify the text, we refer to the combined dextral deformation zone as an abbreviated composite system: Walker Lane Belt, Eastern California Shear Zone, focusing on the cross-cutting Garlock fault. So they combined them together and said Garlock's in the middle.
So put it in English for
now
me.
they're saying, see that.
Yeah, put it in English for me.
Wow. For this study, they're combining the Walker Lane and Eastern California Shear Zone together with Garlock in the middle. So of course, they're focusing on Garlock because it's the monkey fault in the middle. So now they're going to give more stuff. So they'll say now Walker Lane is a 40 to 100 kilometer wide zone of dispersed strike slip, normal, and oblique faulting and associated deformation that is on board of the plate boundary, dextral strike slip, San Andreas fault. So geodetic data show that this zone accounts for a quarter of the active plate boundary relative movement. So we've already heard that 40 times already.
Mm-hmm.
It overprints the distributed normal fault system of the Middle Miocene Basin and Range orogeny and cuts across the Mojave Desert, which only experienced early Miocene extension. The LEC is characterized by a complex system of faults with many different geometry scales and kinematics. And then they say, well, it's focusing in on the sinistral Garlock fault zone where it cuts transversely.
I think that sinistral means in interior. Yeah, the interior of the study focused on the sinistral Garlock fault zone. That means the interior of the fault zone, where the cuts traversely across the faults of the Walker Lane and the shear zone. The Garlock fault zone is prominent structure, but it does not disrupt the overall dextral shear of the Walker Lane California shear zone, which is what we need to talk about maybe in 2 weeks, because we have to finish this one and then go to the ocean again. As demonstrated by geodetic data, the Garlock fault connects southwestward into the San Andreas fault as a conjugate fault. At the big bend of the trace of the San Andreas fault, our group has studied one sites along the central segment of the Garlock fault and to evaluate the interactions in the dextral strike slip faults that intercept the fault. We pursued further study and have accessed the closed access military area to the east. Okay, so they got into the military area. The study explores the new areas of the test of our early hypothesis. Go ahead. You said something.
Yeah, the other new studies we're going to look at. Yeah, the other new studies, the other one we're going to look at, they let them into the military.
The redefined one, July 2024.
Yeah, so it's like the same thing, but we'll talk about that next. Mm-hmm. So it just talks about a lot of the same things again. So it's saying the various fault segments, it can have big quakes, but like where there's breaks and where they divide it up, it could stop propagation of a rupture, they think. So like one section may go off, but it may not move to the other one. So you could have like one section only have a 5 or a 6, for example, like what it did in 92.
Yeah, I'm reading some of the things in here. It says the Garlock Fault is a major left lateral strike slip fault that extends eastward from the intersection with the San Andreas up to Death Valley. It forms a prominent physiographic boundary between east-west extension and the Basin Range province. This is the same article. I think it's just gone into more detail on this one. This is the published article. On the western segment of Garlock Fault, Clark Wash documented 66 million years ago. Offset older alluvial fan, which Garlock Wash has subsequently incised. What is an alluvial fan? That's where a river goes into the sea, and as it distributes outward, it looks like a fan, kind of like the bottom of the Mississippi River, also the delta down in Mexico. Gulf of Mexico, or not Gulf of Mexico, but Gulf of California. So on the western segment of the Garlock Fault, it has that. An older alluvial fan, which the Garlock Wash has subsequently incised or, went through. They determined the offset back slipping a riser between the stream bank, between the older fan surface and the top surface of the younger, incised channel. Something just went off. My monitor just went off. Just got shut off. So I don't know what happened just now. Yeah, somebody's peed-oed on me. But crapola. I don't know what happened. Go ahead. You can continue whatever you want, bud, because we're all right. We're going live.
I'm not going to go into super detail for the rest of this one anyway, because what it does, it goes into each individual fault that makes up Garlock, and it starts breaking
down.
Here for 3 hours, but basically they're trying to figure out what every single fault that's related to that section is slipping at, which is pretty crazy because they're all slightly different, or they're all slipping at slightly different rates. And you'll find that when we do the next one, which is on the because this is what they're finding all the new studies. When they break it down into the segments, they start doing all the faults that are in that slightly different.
Yeah, you're frozen now. Oh, you're all right.
Am I?
You're all right.
Okay, that's weird.
Yeah.
Okay, well, we'll move on to the next study now because it talks about the western and central sections. So that's the next one in the list, which is from this year, 2024.
Unfortunately, I've got a technical problem here. We're okay because we're live outside, everybody. I have to close OBS Studio somehow. And close that. I don't know what's going on. I've lost my monitor. I can't see anything. Yeah.
It's all completely black?
Yeah, it's completely black. And I checked it with, because I have a KVM. I went to the other computer and it works fine. So whatever we're doing here is stopping it. So continue, bud. I'll try to stay with you.
Okay, well, the next study is refined Holocene slip rate for the western and central segments of the Garlock Fault. Record of alternating millennial scale periods of fast and slow fault slip.
And this is the one I was reading off of. Yeah.
Yeah. So I'm not going to go into super detail on this one either, but
want to read the abstract?
They found, it just explains like how they did it.
Non-technical summary. Advanced geomorphic mapping and dating methods allow us to study the Garlock Fault in Southern Cal. Past research has shown that some major faults show irregular behavior over 1,000-year term scales. Specifically, our findings show that during some periods of the Garlock fault has been slipping faster than its long-term rate, and other times it has been slipping slower than its long-term average. These new insights build onto existing data and allow scientists to better understand complex behavior seen in the fault networks, ultimately better informing seismic hazard and assessments. Now, that's something that you and I brought up before, such as, the movement of plates. They say, oh, it's 10 millimeters a year. Okay, it's just a number. Well, that 10 millimeters a year is over 50 million years. There are times that there are thousands of years where, because we're talking millions, right? Now we're talking thousands, a shorter time period, that it moves incredibly fast, and other times it moves incredibly slow. So there are other factors there are other factors in play here that that are transcontinental, and we will get into those at a later date. But as we talk about what's going on here, we're bringing it to your attention that the other continents around the plate, the Pacific plate, will speed up and slow down the movement of faults here in California. I'm not in California, but you know what I mean. So there are extenuating things that will speed it up and slow it down, such as what I always bring up, that there tends to be, somewhere between a 6 and a 14-month swing of the chicken leg, or Mexico swings to the right or to the east or to the left. And I haven't figured out the exact time period, but it seems to do that. And if it does, that means the left side or the Pacific side would be moving faster. And if not, the other side would be moving as well, maybe moving slower, adding more Coulomb stress. Who knows? We'd have to be expanded in those studies a lot more to really dig down into it. But I think that's what this study is trying to say, that there are times when it moves a lot faster and other times it moves a little bit slower. And so they take an average and they apply.
And right now, the western and central sections are moving slightly faster than the eastern section, which is interesting.
The western side is moving faster. I agree. That to me, that would be the chicken leg on moving toward the ocean side. More so. You know what I'm saying?
And the central is moving more since Ridgecrest happened, basically.
Mm-hmm. So it's sped up since Ridgecrest. So Ridgecrest released some stress. So now there's movement that can be more free to move north, is what you're saying, or more northwest.
Yeah, on the central section, anyway.
Yeah, on the central section of the Garlock. All right. And so that means it's moving out toward Barstow. And the northern part would be, which Ridgecrest went actually closer to the ocean. I don't know how many millimeters or centimeters it moved, or maybe even feet. I know the desert moved 15 feet of strike slip movement, but or maybe even 16, but I think it was 15 if I read correct. But it also went closer to the ocean.
And this study goes like super in detail where they're focusing on, and it has all these crazy diagrams, all that, which I'm not going to go.
You're not going to go into too much? Okay.
No, I just basically summarized that. Yeah. So now the next one we're going to do, we're going to start talking about the faults that are way over on the eastern end of Garlock. So we're going to start with Death Valley, because it's all the rage right now.
Oh, yeah.
So,
well, Death Valley had some activity this week, didn't it?
Yeah, and we're going to go into detail on that. But I put the SCEDC.
There you go.
Summaries for each of the faults on that end over there.
I just
so
knocked it out.
Yeah.
Sorry.
So we'll just read them off.
Okay, go ahead. Oh.
Valley fault zone. Type of fault. Right lateral strike slip. 115 kilometer length of zone. Total length of fault segments is roughly 200 kilometers. Now I got to explain this right now because when we get into it, you'll see the breakdowns. So the Death Valley fault zone is made up of 3 main faults right now: the North Death Valley fault, the Black Mountain fault, and the Southern Death Valley fault. So there's 3 that make it up, and then there's another offshoot of it in kind of towards the middle called the Furnace Creek fault.
Yep, which is what just
we'll see that when we get into
the map. Yeah, this last week was the Furnace Creek popping. Yeah. All right, so what's next?
So most recent surface rupture was the Holocene time, they think. So the
roughly 1,000 years ago.
Yeah.
Probable magnitude 6.5.
Slip rate roughly 3 millimeters. Yeah. Slip rate is roughly 3 millimeter a year at south end, considerably less at north. An interval between major ruptures is 1,000 years. Probable magnitude 6.5 to 7.3, but the newest studies I read, they said it can go up to 7.7.
Wow.
Because they've been studying each of these segments, and they're different.
Oh.
The north is different from the Black Mountain section, is different from the southern section. And I'm not going to get into all the numbers.
Okay.
But that's what they found. Now, the next one is the Town Pass fault. There's a reason why I'm talking about these ones. You'll see when we
all right,
better do. Yeah, I'll do Town Pass fault first.
All right.
It's a normal fault.
Why don't we stop here? I guess the stream went down. So why don't you hold on? Part 2 coming up, everybody.